Thank you. So hello, everybody. Welcome to this session. Thanks for joining the session this morning. I'm Zonouz from Georgia Tech, an associate professor. I'm super excited to be here. Grateful to the organizers of CyberCon, lots of energy, the Office of Chief Information Officer, Department of Energy. I'm also grateful that my flight on Monday from Atlanta to Dallas was not canceled based on what we saw last week, actually despite being delayed 3 times. So the second time it got delayed, I booked a rental car just in case. But then the third time it got delayed, I was like, I made a right choice. But then we took off, and then I had to cancel the rental car while in the air. Unlike most of my summer, actually, last week I was lucky not to be traveling, but I felt sorry for everybody whose travel plans were seriously impacted. Watching all that chaos, towards the end of last week, I started kind of a what-if proactive analysis of thinking of or devising plan B and how to get to Dallas in case the flight gets canceled. Essentially to ensure a successful flight despite potential disruptions. And that kind of segues well to the topic that I'd like to talk about today, resilience. The resilience of interdependent infrastructures, and particularly critical infrastructures. So I'd like to share my vision on how to build a cyber-enabled, safe and secure society for the public good, safety, and our national security. So to set the scope, as I mentioned, I'll be focusing on critical infrastructures that, as we all know, provide core societal functionalities. Most of them operate based on cyber-physical systems where IT assets and OT processes closely interact. And due to the complexity of these infrastructures and the sophistications of the emerging threat vectors, the conventional way of looking at security for absolute invulnerability is no longer feasible. That's why through the whole CyberCon and nowadays we've been focusing on resilience, which is to ensure the system's critical services and functionalities despite potential disruptions, either malicious or accidental. So the way I'll present today is to go through looking in the past, the challenges that we faced, and initiatives that we took to address them, the challenges of today, and the concerns of tomorrow that we have to be planning for today. So going back to the CrowdStrike incident last week, what essentially happened was that a single security update that was there to increase our security against potential threats caused massive disruption to daily lives, governments, and businesses without any threat. So a solution in charge of securing a critical sector, air transportation, impacted the availability of its critical services, the flights, without any attack. And despite being an IT incident, it impacted the critical infrastructures, not in one sector, but in multiple sectors, due to intrinsic interdependencies across sectors of critical infrastructures. And that's also the topic that I'd like to talk about today, so resilience and interdependence. So looking in the past, the way we used to handle security was by security by obscurity, to hide the vulnerabilities as opposed to fixing them. We didn't have security standards, or enough of them, resulting in inadequate and inconsistent security. We did not have enough redundancy in the systems that is required for resilience. So operating power grid, for example, next to its capacity, not leaving a leeway in case of a failure to cope with. But also, the vendors of equipment and controllers did not incorporate enough security measures in those devices. Hence, we mainly focused on the perimeter security. But that has been partially addressed nowadays with techniques such as like cryptographic digital signatures and trusted boot and zero trust architectures. But from a broader scope, some of the noteworthy initiatives from decades ago include what-if analysis, the N-1 contingency criteria, to ensure the power systems being operational despite a single failure. That brought some level of redundancy. The best effort guidelines, such as the NIST ICS security, as well as the Purdue model, essentially provided guidelines and recommendations to industry to voluntarily boost up their security. But the bold action by NERC in 2008 to mandate the compliance with the NERC CIP requirements was to essentially ensure the cybersecurity of the power grid. And all this was essentially enabled by funding and support and sponsorship by different agencies in the government. But also from the policy end, the government stepped up. I'd like to mention this report, the PCAS report to the President's office recently, earlier this year, on cyber-physical resilience. So it provides several recommendations. Number one, establish performance metrics. Identify the critical services in your system that must maintain operational. Number two, create a national observatory to understand the strengths and weaknesses of our critical infrastructures. Number three, increase our government's resilience capacity by contributing resources to the sector risk management agencies. And number four, increase the industry accountability by asking the CEOs and executives to contribute resources to ensure our infrastructure resilience. So the White House also released 2 years ago the National Security Strategy to look into these topics from a broader perspective. But also the DOE's report on cybersecurity strategy earlier this year provided guidelines and pillars, particularly understand your risks, mitigate them. Number three, enable mission resilience. Number four, develop cyber workforce for it. And number five, protect our critical infrastructure power grid. So I mentioned that NERC CIP was one of the efforts in the past to address our challenges. So there's been several studies on NERC CIP. An example of those studies include our ongoing effort at Georgia Tech in collaboration with Texas A&M, Kate Davis, and Network Perception, Robin Berthier, where we perform in-depth one-on-one interviews with subject matter experts who have been in direct involvement with standards development, compliance, and auditing procedures. The goal here is to be constructive, and in a couple of months, we will share this report with the community, with industry, government, NERC, FERC, and academia, hoping to be beneficial and useful in cybersecurity of our grid, but also other sectors that have been less mature in terms of cybersecurity. So moving to present, it's been 1 or 2 decades already that we're talking about the disconnect between IT and OT. There's been a lot of tremendously valuable efforts and projects and solutions already deployed by the industry in closing this gap. It's much smaller than before, but still we need fundamental solutions to eliminate this gap, essentially. On supply chain, it's impossible to protect something that we don't know we have. Devices and controllers and PLCs are getting more and more interconnected, which is for convenience, but it also provides different attack vectors and propagation channel for malware. Also enables cascading failures, possibly. Inheriting cybersecurity from IT, the way we've been handling security has been very reactive. In IT platforms, as I'll mention, real-time detection of attacks works. In OT, does not. And human factors was one of the topics that has come up in our NERC CIP interviews. CIP4 personnel and training to be one of the challenging ones to comply with. And I think one of the fundamental reasons is that there is no basic good models to formulate that aspect of usually weakest link in the critical infrastructure from cybersecurity perspective well enough. So I'll mention actually first four topics that I just mentioned. To demonstrate a possible attack vector that crosses the boundary between IT and OT, we showed how a physics-aware malware can first exploit vulnerabilities on the IT side to infiltrate the IT network, and finally infect a controller, a PLC device on the OT side. The physics-aware malware then sits within the firmware of PLC as a rootkit and emulates underlying physical process to mislead what the operators see on their HMI screen regarding what the malware really does on the physical plant to disrupt it, to drive it to unsafe states. Being physics aware, And this is beyond just replaying a previously recorded sensor measurements like the Stuxnet did and the following attacks sometimes also have performed. This is like the malware acting as a digital twin of the physical process. So this physics-aware malware and other past incidents that kind of cross the boundaries between IT and OT indicate the urgent need for hybrid cyber-physical modeling to correlate better the cybersecurity incidents on the IT side and how they may have caused events, unsafety issues on the OT processes. With such solutions, we can perform better detection, better diagnostics, understanding of what happened in the network so that we can respond and recover better, which is important for resilience. We can perform physics-aware risk assessment, risk prioritization, by understanding how difficult different attack paths are and assessing how severe the potential physical impact on the OT process would be if any of those attacks succeed. On the supply chain part, we have performed SBOM, software bill of material analysis on a large number of controllers from popular vendors. Without mentioning vendors' name here for obvious reasons, we had some interesting findings. Different controller models from the same vendor share lots of code and software libraries. A PLC device that you buy today has software libraries in it from 14 years ago, 6 years past its end of life determined by the developers. Two controllers from different vendors share 13% of their third-party components and libraries. And some vendors, instead of updating library dependencies, they bundle multiple outdated versions, possibly to avoid costly unit testing procedures. We also see a lot of vendors performing backporting and backported patches being common, in-house fixing of the issues. And that introduces a chaotic situation for vulnerability assessment ecosystem, because no longer we can rely on software libraries and their versions to determine what vulnerabilities are there, because some vulnerabilities are still there, some of them may have been patched by the vendors in-house, some of those patches sometimes introduce new kinds of vulnerabilities. So the bottom line here, all this shared code and third-party libraries, sometimes developed by unknown sources, introduce yet another vector of interdependence across different controller models of the same vendor, across vendors, and across critical infrastructure sectors. So using a single vulnerability in a popular software library, the attacker can now infect different controller models of the same vendor, controllers across vendors, and it can attack different sectors of our critical infrastructure. Because the same PLC device that we buy today is deployed in the water facilities, the power grid, oil and gas, hospitals, trains, essentially everywhere. And that increases the aggregate exposure of these devices, increases the attack surface for possibly coordinated attacks by the adversaries. As we know, all of these devices are getting more and more interconnected, with lots of functionalities in them to provide internet connectability, even more importantly. Embedded web servers in the PLCs, for example. Essentially, that replaces our conventional firewall-based network segregation security with whatever we can assume from web in terms of cybersecurity, which is not much. So that interconnectivity really increases the interdependence across devices, across networks, and across sectors even further more, increasing the attack surface and channels of malware propagation. Also, the hypothesis is that this would possibly, this interconnectability within these devices would expose these critical controllers in our internet internationally as an unintentional attack surface for adversaries to target. And this is the hypothesis that we exactly studied. So using techniques from AI and tools such as Shodan and Census, we designed automated algorithms to synthesize optimized or optimal queries to scan the whole internet worldwide. As a result, we were able to discover 30 times more controllers internationally compared to past work. And these controllers were in critical sectors, the governments, airports, hospitals, military, so on and so forth. Just to be clear, these controllers were already exposed, so we were the first good guys discovering them. Following that, we conducted a fairly large-scale outreach campaign, reaching back out to the corresponding sectors and operators and the owners. And 30% of those controllers today is taken off the internet. So that is 30% less attack surface worldwide. And this is an active project in my team, and actually I'm really hoping that we can still increase this number. So this whole interconnected devices, again, increases the attack surface, makes us more vulnerable and less resilient. As I just mentioned, inheriting cybersecurity from IT, we are now handling security on the more reactive side. In a purely IT platform, detecting an attack exactly once it happens, it's completely fine, because you can pause a software system. You can pause chase.com web page when a fraudulent activity is detected on its login page. You cannot pause a physical OT process. There's a physical momentum, inertia. So real-time security is often too late in those platforms. There are also solutions to model and formally verify these platforms because they become operational. And such formal methods do not scale up to the complexity level of critical infrastructures. That is why we've been proposing and developing solutions for proactive security, predictive situational awareness, and proactive response and recovery. So essentially, while the system is operating, we perform reachability analysis on the system models, exploring future states of the system, looking for unsafe bad states. And in case we see an unsafe future state, the time gap between the system's current operation point and that future unsafe state enables the resilience engine to decide upon optimal response and recovery countermeasures to deploy if those future bad states get realized. I just mentioned few example solutions here. I just also want to really essentially emphasize that there's been a lot of tremendously valuable efforts, projects, initiatives by industry, national labs, the government, academia, focusing on exact same topics that I talked about, which I couldn't, of course, go over because of time. Now, looking into the future, the emerging technologies and sophisticated threat vectors, again, introduce new challenges for us to focus on. Starting with fundamentals, we just need to do a much better job in teaching. And I do not mean incrementally better. As an example, as we all know, there are almost 500,000 open job security positions nowadays in the US. Yet, not all 24,000 cybersecurity graduates can find jobs. Why? Because of the skill set gap between what we educate and what the real world needs. It's impossible to talk about future concerns and not talk about AI. The revolutionary AI technologies and Gen AI is already transforming cybersecurity and resilience landscape. Particularly, the complexity of AI is increasing the asymmetry between attack and defense in that interaction, not in our favor. Because to defend a system, you need to identify and cover all the holes and vulnerabilities in that system. But to attack, you need to find only one hole. And AI models nowadays are just full of unknown holes. 20 years ago, we had difficulty transforming from simple deterministic systems to general adaptive systems, such as general purpose operating systems and web technologies. Now we have to prepare to adopt AI models, orchestrated AI models working together, interacting with each other, possibly towards a safety critical mission. So expecting 100% safety guarantees, provable properties about those systems is unrealistic. That's why initiatives such as NIST on test and evaluation of these AI models is crucially important. Also, there are solutions, especially in our domain, making AI models more domain-specific, such as physics-informed neural networks, and bringing humans in the loop or on the loop, as opposed to making AI solutions completely autonomous, are very beneficial. But also in parallel, we have to principally change how we approach the problem by engineering system designs in such a way that the system can cope with and tolerate potential and likely AI failures in the future. I mentioned how supply chain introduces cross-sector interdependence. Also, as we know, different sectors of critical infrastructures depend on each other in terms of functionality. The water facilities depend on power grid, the power grid depends on manufacturing, and so on and so forth. So resilience of one sector profoundly impacts others. So for instance, a power grid attack may no longer originate from internet, but it may be due to a cybersecurity attack in a remote manufacturing facility that happens to be producing transformers. In terms of complexity, I talked about AI models. The cross-sector interdependency is yet another vector of complexity. I talked about controllers and PLC devices are becoming powerhouse of functionalities and interconnected. All these lead to over-complex systems without much on the solution end. And I'm talking about complexity of not only the target systems, the critical infrastructure, but complexity of the security solutions that we designed to protect the target system. Kind of related to the CrowdStrike incident, where the security solution disrupted the target system's operations without any attack. On the education side, I'd like to highlight this invaluable effort by the Idaho National Lab, the CIE, Cyber Informed Engineering, that principally transforms how we are looking at the cybersecurity from conventional IT platforms to now engineering systems, using principles, some of which are listed on the slide here. So we are a part of the team, but also we are leveraging these principles and CIE program at Georgia Tech in our master's program for cyber physical system security, which focuses on critical infrastructure resilience. So we recently revised the curriculum of the program to make it CIE compatible. It's a 32-credit program offered on campus and online in asymmetric way, enabling professionals remotely to enroll and get their degrees while performing their daytime job. Some of the courses from that master's program are listed here. The critical infrastructure security. It's a non-technical course where from the policy side, from top-level view, we look into past incidents, both malicious and accidental, how they impacted different sectors of critical infrastructures, how they exploited or leveraged the interdependencies across the sectors, how they impacted the functionalities of our society. So we start with 9/11 attacks. We look into 2003 blackout and Colonial Pipeline and Texas freeze and the Russian attacks against Ukraine, both military and cyber attacks on critical infrastructures. The second course, Intro to Cyber Physical Systems, is a technical course on industrial control systems security. It includes topics of OT, IT, and how they interplay. It includes hands-on projects on programming PLC devices and the security of those devices and how attacks are performed in those networks and how defenses should be designed. For that also, we have been developing test beds. We already have the power grid test bed. We recently finalized the maritime test bed that you see on the slide, and also digital twins like the GR-Fix test bed that we are leveraging in the course. And finally, the cybersecurity of drones, as you see on the top right of the slide. It's a very technical course where students get drones in pieces, get the firmware in different modules. They have to compile everything. They have to assemble the drone. They have to calibrate the drone. And the syllabus is a multidisciplinary syllabus. Includes topics from control theory, system identification, and transfer functions, and PID controllers, all the way to cybersecurity topics. The reverse engineering, malware analysis, attack and defense, and detecting attacks. And it has both class lectures as well as outdoor flights, as you see, where students in interactive game, competitive game environment, two teams design attack and defense and against each other on the actual flying drones. One thing about this course is that more than half of the course are female students, which is very encouraging. On the cross-sector resilience, or the exact topic that I talked about today, at Georgia Tech, we also identified the problem and as a crucially important one, so much that we started this program, SCS, Security of Engineered Systems, to focus on exact same topic. It has 3 pillars of research, education, and testbed. And we already hired one tenure track faculty professor at Georgia Tech last cycle, and we have more than 4 open tenure track faculty to be focusing on these topics to hopefully next cycle hiring. So almost all I talked about is done by my research group, Cyber Physical System Security Research Lab at Georgia Tech. I'm also thankful to the organizers of the event, CyberCon. Again, as I mentioned, lots of energy. The sponsors, Department of Energy, National Science Foundation, my collaborators, and the facilities within the Georgia Tech that enabled all this effort. So essentially, to close, I'll reiterate the main points I mentioned. To engineer resilient, interdependent infrastructures, we need to identify the critical services in our systems that must maintain no matter what. We need to know we want to be resilient against what? Identify the risks. What attacks we want to protect ourselves against? What failures are we concerned about? And in order to understand their impact on our system, we have to understand our systems better. Interdependencies that are existing in our system currently. Any resilience requires some sort of redundancy, functionality, equipment, or maybe hardware, software, or capacity with some level of diversity. And such a redundancy is usually costly, that requires business decisions on the side. And on this, from the ethical perspective, on this particular direction of critical infrastructure resilience and security topic, we have to approach the problem with responsible engineering mindset. System designers nowadays have lots of power in their hands. The decision that they make today has impact on human lives down the line. So any decision they make during design time should prioritize not only professional codes of ethics, but the public safety, public good, and national security. And obviously, this is all enabled by the topics that we already have been talking at CyberCon this week on providing synergistic collaborations and multidisciplinary initiatives, efforts such as JCDC and bringing the public-private sectors together, and with fast spreading technologies such as AI nowadays and cybersecurity, it's super important to have accelerated tech transfer initiatives to take research solutions from academia to industry and practice. Well, that's pretty much what I had to say. Thank you so much for your attention.